Then it is transcendental functions. Now what are the transcendental functions? Functions that are not algebraic are called transcendental function. In mathematics, a function not expressible as a finite combination of the algebraic operations of addition, multiplication, subtraction, division, raising to a power and extracting a root. It is opposite to the definition of an algebraic function. You can express algebraic function as a finite combination of the algebraic operation, but you can't express your transcendental function as a finite combination of the algebraic operation. The functions such as all trigonometric functions, hyperbolic functions, exponential functions and logarithmic functions are called transcendental functions. Or we can say that these are all examples of transcendental function. If a function involves any of these functions, then that function is known as transcendental function. Let's see a few examples of transcendental function. Log of x, sine of x, cos of x, e to the power x, and any functions containing them. We can say that any function which is containing any of these functions, that function is known as transcendental function. Then it is trigonometric function. Trigonometric functions are the functions sine, cosine, tangent, secant, cosecant, and cotangent. The word trigonometry is derived from Greek words which means triangle measurement. Although trigonometry has been organized into an abstract mathematical system, much of it is still concerned with the triangle measurement. And you have discussed this content completely in your class first year. Now let's discuss what is the definition given here. Trigonometric functions are elementary functions, the argument of which is an angle. The trigonometric functions describe the relation between the sides and angle of a right triangle. So whenever we are dealing with the three sides and three angles of a right angle triangle, we are dealing with the trigonometry. And the function is known as trigonometric function. The trigonometric functions include the following 6 functions, as we have discussed right now: sine, cosine, tangent, cotangent, secant, and cosecant. For examples, f of x equals to sine x, cos of x, tangent of x, and you can also express their reciprocals, that is secant, cosecant, and cotangent. Then it is exponential function. What is an exponential function? The exponential functions are the functions of the form f of x, which is equal to a to the power x, where the base a is a positive constant. Note that these functions are called exponential functions because the variable x is in the exponent. You can see that x is given in the exponent and a is its base. So that is why such a function is known as exponential function, in which the variable is given as an exponent. Now what are the properties of exponential function? The properties of exponential functions are summarized here, where y equals to f of x and it is equal to b to the power x. In this exponential function, b will not be equal to 0. It will be greater than 0 and b will not be equal to 1. The domain will be all real numbers, but its range will be only positive real numbers. It will pass through 0, 1. It is continuous everywhere, or we can say all graphs are continuous curves with no holes or jumps. If b is greater than 1, it is increasing on this interval, and if the value of b is less than 1, it is decreasing on this interval. It means b of x increases as x increases and b of x decreases as x increases. You will understand this point number 5 later on when I'll explain you the growth and decay of exponential function. This point, when b is greater than 1, it represents the growth of an exponential function, and when b is less than 1, it represents the decay of any function. Then graph of exponential functions when a is greater than 1. How will you examine the graph of an exponential function when the base a is greater than 1? That is, the graph will be an increasing function, right? See, it is passing from 0, 1. It is a continuous curve with no holes or jumps. This graph represents the growth of a function since it is increasing. The domain is from minus infinity to infinity, and you can see that its range is only positive real numbers. The next thing is it has horizontal asymptote at y equals to 0. Now what is horizontal asymptote? Horizontal asymptotes are horizontal lines the graph approaches. You can see that the graph is approaching this axis, x-axis, so we can say that it has horizontal asymptote. The horizontal asymptote is the x-axis, so y will be equal to 0 here. Graph of exponential function when a is less than 1. This graph represents the graph of a decay function. The previous graph represents the graph of the growth function. Here, since the graph is decreasing, you can see that the graph is decreasing when the value of a is greater than 0 and it is less than 1. Again, its domain will be from minus infinity till infinity. Its range is from 0 till infinity, and it has horizontal asymptote at y equals to 0. Again, the graph is approaching x-axis. It will approach x-axis, but it will never reach the axis, right? So I hope that you are clear with the graph of an exponential function. Now, exponential function using example. Here is the example. I'm going to plot the function y equals to 2 to the power x. Since x is given in the exponent, that is why this function is exponential function. We are going to draw its graph. You can see that the graph is a continuous curve and it is passing from 0, 1. The graph of y equals to 2 to the power x, it is 2 to the power x, is shown to the right. Here are some properties of the exponential function when the base is greater than 1. You can see that this base b is greater than 1, so the graph will be increasing. It will represent an increasing function. The graph passes through the point 0, 1. Do you all agree with this point? Is it passing through 0, 1? Yes, it is. The domain is all real numbers. You can insert any value of x. You will be getting some output, but the output you will be getting will be positive real number. The range is y greater than, y is your output and it will be greater than 0. The graph is increasing. Yes, it is increasing. It is increasing. And the graph is asymptotic to the x-axis. It is approaching x-axis. So we can say that the graph is asymptotic to the x-axis as x approaches negative infinity. The graph is continuous. The graph is smooth. After explaining this example of an exponential function, I hope that you are clear with the basic properties of the graph of an exponential function. Let's take example number 2. Sketch the graph of 2 to the power x. I'm doing the same example, but I'm taking the table. Here is my input. As I've told you before that you can take any real value as your input. As a result, you'll be getting some output. Then plot these points on a Cartesian plane. Join those points. Finally, you'll be getting the graph. I'm explaining the same question in different ways. Then here comes the last article of our today's lecture, that is laws of exponents. The laws of exponents are explained here along with their examples. If a and b are positive real numbers where a is not equal to 1 and b is also not equal to 1, then the multiplying powers with same base. First law represents multiplying powers with same base. In multiplication of exponents, if the bases are same, then we need to add the exponents. So here is our base. The bases are same, so we can add their pairs. Then the second law is dividing pairs with the same base. In division, if the bases are same, then we need to subtract the exponents. You can see that here the bases are same, so we need to subtract the exponents. The lower exponent will be subtracted from the upper exponent. Then the third law is, it's the pair of a pair. In pair of a pair, you need to multiply the pairs. You can see that it is pair of a pair. So you need to simply multiply these two pairs. Its fourth law is multiplying pairs with the same exponent. You can see that the bases are different, but the exponent is same. So we consider the product of A and B, which have different bases but the same exponent. The exponent is x here. Then the fifth law is, for division with like bases, you subtract exponents just as for multiplication of like bases, you add exponents, right? But there is no need to memorize a special rule for division. You can always work it out from the other rules or by counting. In the same way, dividing different bases, here the bases are different, it can't be simplified unless the exponents are equal. So here you can combine like exponents even when the bases are different. Here I have solved few examples for you using these laws of exponent. I want you to solve them on your own so that you can have a clear idea how to apply these laws in your exercise problems. This was all about our today's lecture. Hope you are clear with all the concepts. Thank you so very much. Wish you good luck.